and then I say equals maybe we'll simplify this. So what we've got is here's our r of t function. Here's our derivative. Here's our second derivative, which is taken by product rule. Derivative of this times all this, plus this times the derivative of all this, right? And this is what we get, okay? And it's very straightforward. Now this thing is squared, so we'd probably write it as pi squared over 4t, right? But that's just a coefficient. We'll look at that in a minute. So what is this telling us about the motion? Okay, well, first of all, this is an ellipse, okay? R's of the form x times I plus y times j, with x equal a times the cosine of this thing, and y equals b times the sine, right? So x squared over a squared plus y squared over b squared equals 1. And your picture is an ellipse with a semi-major axis of A and a semi-minor axis of B. We'll go the rectangles in A, and maybe we can get a decent looking ellipse. Okay? I was trying to avoid the B there, so that got a little lopsided.
What does the square root do to the ellipse?
It changes the rate at which you go around, and that's what we're going to talk about. Okay, but first place, there's your path, and it's always the same. Now, since I left the I and the J off, you could have treated this, and would have, if you did exactly what I wrote, as a polar function, okay? And that would have been totally valid, since that's the way I wrote the thing, okay? Mistake on my part. But let's look at this function. Now, the derivatives are straightforward. There's nothing to that. Now, of course, you want to practice a little bit and get the rust out if you're a little rusty with derivatives, okay? And that's why you'll have a lot of problems to do. Fair enough? But the derivatives are very straightforward. It's just derivative of the power function and the product rule and the chain rule, okay? So there's nothing to that. You just keep your wits about you and apply the rules. But we want to see what all this is telling us, okay? So this is the velocity function, and it's a derivative of the r function. Well, as we saw before, if your r function is here at t, and it's here at t plus delta t, then here's your change in r, right? And the change in r, well, r prime of t is the limit as delta t goes to 0 of the change in r over the change in t. And we can see that in the limit, this vector will somehow approach this vector, right? But here's your delta r, and maybe here is your path, okay? Delta r is already pretty close to the path, but it looks like maybe it's diverging a little because the path is curved the way I've drawn it. But in the limit, the delta r becomes parallel to the path. So that's your v of t is always parallel, well, tangent to the path. Now, there are assumptions. We've got to assume this function is smoothly differentiable and stuff, okay? But under those conditions, we've now defined a path, and we know what the path is. It's an ellipse, okay? And if we want to get the function, I drew these pictures last time. It's like here's your r, and here is your v, right? Now, where is your acceleration? It's clear that the v is tangent to the curve. In the examples we did earlier, you were on a circle moving at constant velocity, and we saw and proved, and you need to be able to prove because it's important for physics as well as this, that the acceleration is then back toward the center. It also has magnitude v squared over r. I think I mentioned that. But yeah, we'll see that in physics as well. Okay? In this case, it's no longer so. The reason all that worked before was that you're moving at a constant speed on a circle so that your v was always perpendicular to your r. Because v is tangent, and a tangent to the circle is always perpendicular to the radium. Right? It's not true now on an ellipse. So this has characteristics that we didn't have before. Okay, the other thing that's different from the model that we had before, where we had, the previous model for comparison, it's just a times the quantity cosine omega ti plus sine omega tj. You're on a circle of radius a, moving with an angular frequency omega, meaning that you move around the circle every time omega t changes by 2 pi. T has to therefore change by 2 pi over omega, right? So this had radius a, period 2 pi over omega. Okay? Now what changes here?